Alright, this is video 2 for the lifting unit. In this one we're going to start by talking about something called a scissor lift. A scissor lift is a really cool way of getting a platform from a low height to a higher height. And some advantages, we got a minimum retraction height, so it can go under a lot of field barriers. It smashes down really small. There are disadvantages. They're heavy. They don't do well with side loads. That means if it's fully extended, another robot hits you, you will fall over. You have to build them very precisely. And as you build them taller, their stability decreases. And it's very hard to get them to start moving. So let's take a look at a scissor lift here. A scissor lift is something that can collapse down. So here, we got these arms. And we can consider these levels. So here, this first scissor lift has 3 levels. Notice that one design, we have to have a pivot right here, and we got our motor. So as the motor turns, it applies a force in this direction. And with nowhere to go on this direction, it collapses. And that causes the forces to be transferred into an upward motion. Up here at the top, we have another pivot point. This is where it's attached. But this side right here must be free to slide. Because as this scissor lift gets taller, these two sides are going to collapse as well. And that's something you have to be careful of when you design this. Now down here, this is an example of a scissor lift built, and there's some things I like about it and a lot of things I don't like about it. First off, notice that it's made of bars. Bars are the flimsiest material that we have. I would not recommend building a scissor lift out of bars. It'd be much better to use C-channels or I don't know, something with a little more torsion strength. Here we see that we have a motor, and then we have these 2 gears here and here. It's really hard to get those gears to line up. I think a better design would be to put the motor up here and have it driving gear somewhere there. In fact, if you had the wires for it, you could have motors working together on different parts of your lift. That's if you have the extra motors to spare. But this is a unique design, and there's some things you can learn from it. We tried to build this in a previous year, and it just didn't work. It would work part of the time, and then these gears would start jumping off the track, and it wasn't as easy of a build as you might imagine. Okay, so the next thing I want to talk with you about is some of the math that we can do. Because once we build a lift, we need to be able to figure out how much it can lift. So when figuring out how much weight a motor can lift, torque is an important thing in our calculations. And remember, torque is a circular force. It's a force that, when you apply it to a wheel, it causes a force on the ground. So torque is like a rotational force. So as a quick review, if we have our wheel here and there's a torque applied to the wheel, torque equals a force that's perpendicular to a lever arm. So here the lever arm will be the radius, and we can see that it applies a force to the ground. And notice that the lever arm will always be perpendicular to the force. So this torque would equal the applied force times the radius of the wheel. And this wheel could be a gear if we wanted. So let's take a look at this problem here. We want to be able to calculate how much torque is needed to lift up this weight. So let's say we have a 30 Newton weight. Our value for R is 0.5 meters. That's our lever arm. And we have a VEX 393 motor with an unknown gear ratio. Well, torque is force, which is perpendicular to your lever arm. So in this problem, our force is 30 newtons. That's what we need to lift. Our lever arm distance is 0.5 meters. So we would need 15 Newton meters of torque to perform this operation. Well, if we look at our standard 393 motor, the stall torque is 1.67. So we don't have enough torque. Well, the mechanical advantage will equal the output torque divided by the input torque. So we're looking at a mechanical advantage of at least 9. And we can get that through some gearing. We would have to use a compound gear. If we used non-compound gears, the greatest we can have is between the 12 tooth and the 84 tooth, which is just a mechanical advantage of 7. So we're going to need compound gears to help us with this. But it can be done. So that's what we would need to operate this lift. All right, let's take a look at another one. Let's say we have an elevator. And we want to figure out how much how much we can put on this. And again, it's going to depend on the size of the gear. So let's say we have one motor. So that means our input torque is 1.67 Newton meters, and that's the biggest that we can have. Let's say we are using a gear, and let's say it has a radius of 4 centimeters. Seems about right. What I want to know is how much load I can put on this, or how much force can it pick up. Well, if I look at this, here's what I have. I have my rack and pinion set up. So I can set it up like this. So I have, as this motor turns, I even got my arrow in the wrong way. As this motor turns, turn this way, it would climb up that rack and pinion. So the force would equal the torque divided by the radius of the gear. So that force then would be 41.75 newtons. Now that seems like a lot, but remember, at the stall torque, 1.67 Newton meters, all motion stops. So yeah, we can, if it were resting there, it would hold it, but it wouldn't be able to move it any further up. Also, that force has to take into account the weight of the structure. So it's how much the motor weighs, how much the materials weigh, how much everything weighs, plus whatever package you choose to put on that platform. So 41 newtons seems impressive, but it's really not as much as you would plan on having. All right, that concludes video 2.